What's going on, everybody? Brian Mann here, hands-on auto training. Once again, everyone, we have the simplest root cause causing a very complex situation. In today's instance, we've got ourselves a 2009 4D series. This is a no crank. I got called out on September 20th, 2023 to take a look at this thing for a no communication issue. The interesting thing is we do have communication, just not at the right time. This vehicle had been gutted. I mean, the technician was trying really hard to solve the problem, and as always, it's the very basics. I mean, a simple root cause causes the most complex situations going on. So today we're going to go ahead and take a look on the bench here. I made a little demonstration board, very simple demonstration board to go ahead and use a picoscope and also a multimeter to take a look at what's going on. But what you're going to see here is that using a test light just doesn't cut it. Understanding the basics of electricity and electronics can really show you why we're having all these problems. So let's go ahead and take a look here at this situation. We got a no communication issue on this 2009 4D series. We've got multiple DTCs set here. We got the B10DA, that's a PATS target identifier, not programmed. If you look up the service information for these codes, we'll go through it quickly. On the premium membership site, we go into more depth. We're just going to go over it quickly here. We had a U0300 internal control module software incompatibility. We had a 420, not worried about that. 430, I'm not worried about that either. We also had this P060A internal control module monitoring performance. Very interesting code, and also a 1602 immobilizer ECM communication error. So as you see, we have a lot of codes going on here, and getting a diagnostic path or direction can be very challenging and confusing. This B10DA 51 PATS target identifier, not programmed. If you look at the flow chart, basically it says do a parameter reset. That's linking the IPC and the PCM to do a handshake. What we're talking about is as you turn the key on, these two communicate with each other and they do a handshake, and that allows the vehicle to start when it sees the proper signal from each other, or passcode, or whatever you want to call it. So in this instance, I started right off the rip doing a 10-minute parameter reset, or should I say a PATS learn, and then I did a parameter reset as I was looking up this other information. So as we continue on here, you can see we also had a U0300 AF, internal control module software compatibility. This is all data service information. So let's take a look at this and see where it leads us. You're going to see that it says incompatible software levels within the powertrain control module. It also says that the ETC system uses multiple processors within the powertrain control module, and they each have their own software. So these modules have to communicate together within the powertrain control module. And if they don't communicate, you're going to get this code, and that's kind of what was going on here. It leads us to go to pinpoint test QE. We go over here, and let's see here. Hop into pinpoint test QE, and they say, are there other codes than the following? And yes, there was. We had a P1602 sitting, if you recall, and also the 420 codes, not worried about that. But so we do have other code settings, so we gotta go check out these other codes, just so you know. We'll run through them quickly. You can see here that we have this B10DA 51. There's no PCM ID stored in the IPC. Carry out a parameter reset. So once again, they kind of got us going a long way around here, and I'm already doing that parameter reset. And we have this P060 alpha, and this is the control monitoring performance. Let's take a look at this. Where does it lead us? It leads us to the possibility of a damaged PCM, software incompatibility issue, and also leads us back to our pinpoint test QE, which I'm not thrilled about that. We also had a 1602, a mobilizer ECM communication error. It says that during each vehicle start sequence, when the key is turned to the start or on position, the passive anti-theft system transceiver reads the PATS key, which this vehicle just has information stored in a cluster, and it sends that from the cluster to the powertrain control module. It says here if there's no communication on the high-speed controller area network, this code can set, these other codes will set. and you'll get the 1602. So we've got a lot of different codes to look at here, but like I said, it comes down to a simple situation as usual. Now, I was talking to the customer and I was getting kind of thrown off. I'm thinking, oh, this thing might have a computer problem. All these internal software communication things, it's got a new computer. They had two computers there, so it's probably not the computer. The customer also had the harness tore apart looking for a high-speed communication error. I mean, they had this thing gutted, and I feel bad for him because he was trying really hard to solve the customer's problem. Once again, it's always back to basics. I was about 50 minutes into this thing. I'm like, that's it. I'm checking powers and grounds. So here we go. We've got ourselves our diagram. This is a diagram from AllData, alldata.com, just so you know. I want to take my multimeter and check for power. I'm going to go ahead and ground my multimeter. Always go to battery negative. On this Ford, that was very easy because the battery's right up front. And I go to my ground. What would you think would be a good reading here? We want low voltage, right? So I had 210 millivolts. I'll be the first one to tell you that's a little bit on the high side in my brain, but 210 millivolts is what I read. I'm just sharing with you what I had there. So I just went ahead and said, well, 210 millivolts, that's not a big deal. Let's keep on going. I go over here to power. If you follow this diagram up, you can see this is when the PCM power relay over here is energized. What should we have? Well, I had 13.3 volts. I did have a maintainer on this vehicle, so this was a good reading. Now I go over here, and if we had 13.3 volts on this power down here, what do you think we should have on this power? Well, I had 12.4 volts. So I'm like, interesting. 13.3, 12.4. Now at this point, for those of you that like to load circuits, and we talk back and forth about test lights and all that stuff, I don't actually have a physical test light that actually, you know, has the lead or the probe and all that stuff. I do carry some 194 bulbs and some other bulbs if I really need to load something up. I usually like to let the load be the load, but in this instance, we saw a difference in voltage between one power input and another, so I was like, well, with my lead stuck in here, let me go ahead and add a little bit more of a load. So here we are. I take a light bulb, and if we were at 12.4 volts before, I hook up my little light to ground, and I touch on my multimeter lead back here. What do you think we should have? If we had 12.4 before, we should maintain 12.4. Well, now it dropped down to 9.8 volts. So I know for a fact I've got myself a voltage drop. There's no doubt in my mind that as we're increasing the load, we're trying to put more of a load on a circuit, which means more current flow. If we increase our current flow, our voltage drop is going to go up over even a normal piece of wire. But if we have a bad section in the wire, we're going to see a really big voltage drop. And that's what we're seeing here as we load this circuit up. So you can see we've got this fuse F54 10 amp, and I forgot to mention to you all, I did run through all the fuses on the underhood fuse block with my multimeter real quick. I always do that if I'm having weird situations, just hit them all on top with the key on, and it was all good. But this F54 10 amp fuse over here, I go with my multimeter to ground again, and on this side, what are we expecting? Well, I had 13.3 volts, that's good. And on this side, what do you think we should have? Well, 13.3, right? All right, so moving right along, I go to the back side. We had to flip this fuse block up, and over here I had 12.4 volts. So just so you all know, right in here, there was a issue somewhere. Now, I removed that fuse and put that fuse back in, and I hate to tell you that the problem went away. The fuse had a very odd brown tarnish to it. I've never really seen, well, I might have seen it, but I've never seen it like this. It wasn't rusty. It wasn't like a corrosion type of thing going on. But once I put that fuse back in and I cycled the key, everything like came to life. You could hear the throttle body click, all kinds of things were happy. The vehicle started up and ran. So what do you think was going on with this voltage drop? It's very interesting to think about this, and this is what I want to talk about. This is kind of why we're here, because we have our demonstration board over here, and I do believe that it all comes back down to basics. Just so you know, I have a boatload of capacitors here, and I also have a actual 194 bulb tied into the circuit. We also have a little voltage regulator and an LED. So turning this circuit on with the switch in the down position like this, you see the LED lights up, and we have our 194 bulb light up off of this board. We are probed in here with our scope, but this is going directly through. Power comes in the middle, battery positive, and then goes back up to here. If I go this way, we're running this same power that comes into the center post here. We're going to run it through two 1 ohm resistors. Now you may be able to tell a difference, but I don't see a difference with my eyes. Maybe just a tiny bit. Going this way, it's a little bit less dim, but you see our little 5-volt regulator, it doesn't care which way we go. Let's take a look with a voltmeter. I want to show you guys something with a voltmeter. I'm going to hook up my multimeter to ground here. Let me just get that. And my other lead, I'm going to hook it right into our power supply here. So when I flip this switch, so taking my multimeter here, when I flip the switch one way, we have 12.2 volts. If I go the other way, I have 12.68 volts. 12.68, 12.2, not a big difference. What does this look like when we're trying to charge up a bunch of capacitors? We have to get the scope out to see this. So I'm going to go ahead and hook my scope up to ground here. And I'm going to take my other lead and go right to the power input to our little module that we have. If I can get that on there and get it to stay. We have our same setup. Let's go ahead and get our picoscope out. And just so you guys know, we have our amp clamp here. I'm going to go ahead and zero it so we can go to our probe and hit the zero offset. So I zeroed my picoscope. Let me clear out my rulers. And we have our voltage here. Our blue lead is our voltage at our module, and our red lead is our amp clamp at the main power feed. So let's take a look at what happens. I'm first going to hit this thing with a no fault. So that's no fault. And then I'm going to go ahead and hit it with a fault. I'm going to hit the stop button. Let's take a look what's going on here, guys. First of all, let's take a look at our voltage here. We got about 12.3 volts is what I'm reading on my input there. This is with the fault. And our current, what is our current at this point on our channel B? It's peaking at 5.4 amps, give or take. And down here, you can see it's 0.3 amps, give or take. Let me go back in the buffer, next page over. Oh, look, the voltage actually is a little bit higher in this situation. Not much, just a little bit, just like we had seen before. But what's really going on? I want to take a look at something different that you may not be used to seeing. I'm going to zoom in right in on like one of these on situations. As this circuit gets turned on, I want to zoom in pretty good here. First of all, you can see we have some switch bounce. That's kind of normal with my cruddy switch. Let me go over to the other section over here. I'm going to panhandle all the way over, actually go back out. Let me zoom in on this section over here. This might be better because we had quite a bit of switch bounce in there. And this bounces too, but that's okay. We're going to drag this over so everybody can see what I'm doing. I want to know how long does it take from the time that this is turned on to the point that we get to 9 volts. Let's just take a look. So I'm going to go ahead and type in 9 volts on my one cursor. Let's say 9. So this is 9 volts right here. And we can go ahead and zoom in even more. Just take a look what's happening. So you can see that we're over 20 amps on our amperage scale. Very interesting. And we did have quite a bit of switch bounce there. You know, from 0 to 9 volts. How long does this take? From the second that I turn the switch on to the time that we get to 9 volts. So I would say give or take right there to 9 volts. I'm reading 692 microseconds. That's 692 millionths of a second. So we hit the key, boom, the module powers up, our PCM. What does it look like if we go back to our other situation here when we had a bad problem? I'm going to go back to my other buffer. And I'm going to go ahead and zoom in on this, just like we did before. I lost my amperage. My amperage was so down compared to the first time, right? How long does it take us to get to 9 volts from the time we turn the switch on? Let's find out. So here goes our turn on right there. And here is our 9 volts. That's 14.5 milliseconds. So we went from just above half a millisecond to 14 milliseconds. Wow, 14.5 milliseconds. Guys, this is a long time in computer world. So as this vehicle is keying up, you know, we probably have the key turning on and the cluster's coming right to life really quick, but the PCM's kind of lagging behind. Not to mention all those other internal processors within the PCM. Some of them might be powered up by different circuits, that other power input that gets us 13 volts with no restriction in its current flow, so those capacitors and circuits and electronics inside can turn on immediately. Guys, I really feel that having a basic understanding of basically this is what you call a resistance capacitance circuit, the very basics. I mean, it gets way more in depth than this, but understanding the very basics can help you understand what's going on in a car. This turned out to be a simple voltage drop. Really nothing much going on here, but once again, simple things cause complex problems. So once again, basics lead the way. Hope everybody out there is doing well. If you like this content, please do like, subscribe, hit that notification bell. You know what to do. I do appreciate all you out there to comment on the page and the YouTube channel and everything else. If you want even more in-depth learning on basic electricity, using a picoscope, using snap-on scope, diagnostic testing procedures, programming and stuff like that, be sure to check out the membership site at Hands On Auto Training. $10 a month gets you access to the core subscription, which has a lot of video content, and I think about 40 hours is up there or so now. And then the premium membership for $30 a month gets you 2 live interactive meetings per month. They're Zoom meetings, usually 8 or 9 o'clock Eastern Standard Time. We get together with some smart people. I'm telling you, a lot of the people that attend are very smart, intelligent people from across the country that we get to interact with. I usually present 1 or 2 case studies. We play with scopes. We do all kinds of stuff. But if you're interested, be sure to check it out. Let me know what you think. You guys have a great day. Bye-bye.